Good evening, and welcome to the Scientific Adventures of Beardman. Today we're going to take a look at galaxies. So let's start by defining one. A galaxy, loosely defined, is a group of billions of stars held together by gravitational attraction. Now, some things we consider galaxies have less than billions of stars, even as small as 1,000, which is pretty small, and up to 100 trillion. Now, how many of these galaxies are there in the universe? Well, keep in mind, first of all, we can't observe the whole universe. We can only see a small part of it. Well, we can only see the part of the universe we can see. Of the observable universe, there are approximately 170 billion galaxies. Now, probably best guess, it's really between 150 and 200 billion. Could even be a little bit outside of that range. But 170 billion galaxies in the observable universe. Just to give you an idea, the HUDF recently looked at a spot of the sky that was about 1/10 the diameter of the moon. Okay, so picture looking up at the moon, 1/10 of that diameter, a little circle, and it studied it for 12 days and discovered 10,000 galaxies in that much time. Okay, that's an incredible number for that small amount of time in that small amount of space. So it gives you some concept of how many galaxies there are up there and how many you're looking at any given time when you're looking at a small section of the sky that you can't see because they're so far away, so dim that our eyes can't pick it up without the aid of a telescope. So some galaxies are small as 1,000 stars, up to 100 trillion stars being the largest galaxies. Smallest galaxies are about 1,000 light years across, whereas the biggest ones up to 300,000 light years across for one galaxy. Our closest galaxy is, of course, our own galaxy, the Milky Way. We'll come back to that in a moment. And the farthest one that we've discovered so far was discovered 2 weeks ago on Cinco de Mayo. So I'm sure they considered naming it Puebla after the Battle of Puebla, or Margarita, or Piñata, I'm not sure. Mariachi, wonderful ways to celebrate a new discovery on Cinco de Mayo. But alas, they decided to name it the thrilling name EGS-ZS8-1. I know, really rattles your mind how exciting that is and how proud the father of that must be to name it. Anyways, all right. So this galaxy was discovered. The light has been traveling to us from it for 13.1 billion years. Yes, in a universe that's 13.7 billion years old, it's been traveling for 13.1 billion years. We believe it's about 100,000 years old. 100,000 is incredibly young on the scale of the age of a galaxy. At the particular point in time that we're seeing the light from, in other words, 13.1 billion years ago, this galaxy was gaining new stars, forming new stars at a rate of 80 stars per day. To give you some perspective, our Milky Way galaxy forms 1 star each day. Okay? So, let's talk about the Milky Way for a little while. First of all, it was discovered and named thousands of years before we knew what it was. We just saw this milky band across the sky. And so it was kind of milky looking. It was white, looked kind of like clouds. So it's called the Milky Way. And so you can see it here pictured from Earth. This is, if you go out and you look up in the sky, this is what you see. And this band, it turns out, after Galileo pointed his telescope at it and began to look at it, realized that instead of just being some sort of cloudy substance, it was actually billions of stars. So what does our galaxy look like? Well, from inside it, it looks like this. It's kind of a strip we see there. Well, what gives you that kind of shape? Well, essentially, if you're inside a pancake. Okay, if you're inside a pancake, you can look up You see outside the pancake very easily, so you don't see much of the galaxy. You can look down and you don't see much of the galaxy. But if you look right across the pancake, you see so many stars in that direction, it'll look milky. Okay? So essentially, the Milky Way is a pancake. Well, as we start to study where stars are and start to plot them into a computer so we can see what it looks like, we see that we actually live in a spiral galaxy that would look something like this from outside of the Milky Way. Now keep in mind, you will never see a picture of the Milky Way from this perspective, okay? Because the Milky Way from one side to the other is about 100,000 light years across. If we tip it on its end, as you see from this perspective, the bulge here in the center, the galactic bulge, is about 10,000 light years from bottom to top. Okay, and on the disk, it's about 1,000 light years from bottom to top. So this is a very thin pancake, 100 times wider than it is thick, except to the bulge. So you notice it's got, as I mentioned, the galactic bulge here in the center. It's got the disk around the side. That disk is made of spiral arms, which are caused by density waves. The stars actually travel in and out of these spiral arms. The spiral arms are kind of like traffic jams. If you look at a freeway, you'll see cars driving along, but when a traffic jam comes along, they're all bunched up, higher density. Okay, and so that's what you see. When the stars travel out of that, they separate back out and they're farther apart. So these areas of higher density waves is where most of the new star formation takes place. Our Milky Way has about, our Milky Way, the Milky Way, to which we belong, has about 200 billion stars, making up a total of about 600 billion solar masses. Okay, and a large chunk of that is in a supermassive black hole that exists in the middle of all spiral galaxies. In ours, the supermassive black hole is called Sagittarius A, and Sagittarius A has a mass of about 4 million solar masses, meaning its mass is 4 million times bigger than the sun. Okay. So let's talk more in general about spiral galaxies, one of the two major types of galaxies. The shape we've already described for the Milky Way. It's got the spiral arms, it's got the galactic bulge. It's also got a halo that I hadn't mentioned yet, the Milky Way does as well. That halo is spherical around the disk, and the halo contains older stars. Okay, very little dust and gas. It's mostly older stars. Whereas the disk contains a lot of dust and gas. It has the materials to build more stars, and that's where the stars are forming. In the Milky Way at a rate of about once a day. Depending on the spiral galaxy, it might be a different rate. The dust and gas in those galaxies is relatively cool. Spiral galaxies often have what's called a bar across the center. If you notice, the galactic bulge here has a little bar thing sticking out the sides, and then the spiral arms kind of begin from there. It turns out 2/3 of the galaxies we can see presently have bars, which has increased dramatically since 8 million years ago, when only 10% of spiral galaxies had bars. Okay, we're not quite sure about what causes spiral galaxies to form. It's one of the main things we're exploring in the field of astrophysics, is the mechanism by which galaxies form. We're not sure if they started from the original explosion of the Big Bang and little bits started clumped together to eventually form galaxies, or if something much bigger formed that then broke apart to form galaxies. Okay, so that's one of the things we're looking for as we point our telescopes towards space. Now, the other main type of galaxy is called elliptical galaxies. Okay, there are many other types of galaxies, such as dwarf galaxies, peculiar galaxies, ring galaxies, lenticular galaxies, irregular galaxies. just a whole variety of them. So elliptical galaxies is the other main branch of galaxies. Elliptical galaxies have a huge range of sizes, from small elliptical galaxies to giant elliptical galaxies, which are the biggest galaxies in the universe. Hundreds of trillions of stars. Elliptical galaxies don't have much dust in between stars. The gas that is there, it tends to be very hot, multi-millions of degrees in temperature. The stars tend to be older because there is so little dust that there isn't much to form new stars, and so there aren't new stars. So all the stars tend to be older stars in elliptical galaxies. One of the current hypotheses is that elliptical galaxies are formed from the merger of two other galaxies. One example of this is in about 4 billion years, based on their current velocities, we predict that the Milky Way and Andromeda will collide. Here's a little simulation of that. We see them over the course of the next 4 billion years getting closer and closer together. As they hit, one thing to keep in mind, galaxies have stars that are very far apart, 10, 20 light years apart. And the stars, our whole solar system, light can travel in a few hours. Okay? And that's 10 years or 4 years to the next star. So as stars in a galaxy come through, almost never will two stars actually collide. They'll just come near, affect each other's gravitational paths, and they'll be flung in different directions. So as we see them colliding here, keep in mind that's not individual stars colliding. That'd be incredibly rare. Far more common is the stars are just being gravitationally affected, and so they're moving in a different path. You see that eventually the supermassive black holes seem to merge, and the stars, having been flung in every which way, find some random orbit around, which is what we see in an elliptical galaxy. So it's entirely possible that 7 billion years from now, the Earth will be part of an elliptical galaxy. What we're watching here is this collision taking place from the perspective of the Earth. Galaxies also are lumped together into groups, which just very quickly could be groups or clusters or superclusters, and those are strung together in what are called sheets and filaments on the largest scale of the universe. Thanks for watching Scientific Adventures of Beer Man. Hope you learned something about galaxies, and figure out what you're going to do with the next 4 billion years before we collide with Andromeda. Think of something to make that 4 billion years worthwhile. We'll see you next time. Bye-bye now.